Hey guys, welcome back to my YouTube channel. So in this last lecture, we have detailedly discussed about the Fermi levels. So in last class, we have discussed about intrinsic Fermi levels, where it lies. So this is the equation that we have came into picture. That this is the intrinsic Fermi level. We have seen in the most of the cases that it will lie at the mid level. But when we calculated using the formula like that from the density of states under the Fermi Dirac distribution function, we have got one value. So from that, if we equate it, we will be getting that the Fermi level will be lying just below by this value, which is this value of difference, which will lie from the mid. But there is one condition. So let me rewrite that formula here so that you will be able to understand it clearly. So there is one significance that we have to understand. So this is the intrinsic Fermi level. So which is E mid minus KT divided by 2 ln. This is not log, it's ln. You have to remember it with the base E. So which is NV. So this is the formula that we got. So which is one of the very important and significant formula. Okay. So now let's see. This is the intrinsic Fermi level. We have seen that most of the time the intrinsic Fermi level will lie at the mid. So the intrinsic Fermi level will lie at the mid of the band if T is equal to 0 Kelvin, NC which is equal to NV, or M, the effective mass of electron and proton are equal. Then we will get into state that EFI which will be equal to E mid. Okay, I'm sure it is understood for you guys, because we know the formula, right? For NC can be written as, so the NC can also be written in the form of NV, which is equal to Mn MP the whole power 3 by 2. So these all are effective mass of electrons and protons. Electrons and holes, not protons, like that way. So this is holes. So I hope it's understood for you guys. So this is one of the important key criteria that we have to remember, that whenever T is equal to 0 Kelvin, NC is equal to NV and Mn is equal to MP. The effective mass of electron which is equal to effective mass of holes, and there is a density states in conduction band and density states in valence band also equal. So if that is the case, then our Fermi level will lie exactly at the mid. Okay. So this is intrinsic. So let's go into N type now. So this is a second type of study which is focusing on N type. Okay. So N, we already got the formula from the density of states and effective mass, the calculation, density of states and Fermi Dirac distribution function. So N which is equal to NC e power minus EC EFN divided by KT, right? So which will be approximately equal to ND, that is a donor energy level atom, if it is an N type. If it is an intrinsic only, we won't be able to do this, but in case of an N type, it will be approximately equal to donor type. So in the charge equality also we have saw this condition. So let's take this case and let's get into the picture. That let's divide by N. So NC by N. Let's bring the e power minus term into another side. So it will be EC minus EFN divided by KT, right? So let's use the ln function here. So ln, and then the last class intrinsic we done, right? Same thing, ln and taking the E outside. So then this will be equal to KT will go into opposite side on ln NC divided by N. So this is the thing that we are getting. I hope this is understood for you guys, right? So it is similar to that. We have done nothing. We have taken ln and bring this term outside and this term here itself. Okay. So we can rewrite this into another one term, because in N type we won't see this N value. So N will be proxy equal to ND, right? So NC minus EFN, which will be equal to KT ln NC divided by ND. Okay, so this is another very important formula. So these all are giving some subtraction, some area of difference. You can see here, right? From here we will be know that ND will lie in this region. So ND, not ND, EFN. So now we are finding out this difference. So how much this area, how much this one, and how this one. So like that way we are finding. So these everything, like in the previous section, this is the first formula, we can take it, and this is the second formula. So these are our formulas that are saying how much is the energy band gap difference will lie based upon the doping and density carrier concentration and also temperature. So everything will be depending on these three values. That is nothing but the particular band concentration and the donor or acceptor atom level concentration and temperature. So these value plays a very important role in the energy level difference. So based on this value, the distance are lying, it may lie here or it may lie here or anywhere. That is based on purely on the concentration level that is happening. So I hope for n-type we got to understand, right? So this formula will be applicable only for the non-degenerated semiconductor. Okay. So in order to get the degenerated semiconductor, we know the condition that the concentration of Nd should be much greater than concentration of Nc. So this is the thing, the criteria to get degenerated semiconductor. So degenerate semiconductor. Even we can say degenerated n-type semiconductor. Okay, this is one important term, you can note it. So difference between non-degenerated and degenerated. Okay. So let's get into p-type now. So similar to the n-type, let's use the p-type formula. You guys can even try as a homework, pause the video and try it. So if you guys able to do it, then you are on a very good understanding. I'm appreciating it. So let we know the p-type formula, which is equal to nv e power minus EFP, Fermi level of P, minus EV, valence band, divided by KT. The same thing. This will be proxy equal to NA. This is a P which is proxy equal to NA. So let's divide NV by P and take a ln and remove the values. EFP minus EV divided by KT. Okay, so let's take ln and remove the KT to that side. So EFP minus EV, which will be equal to KT ln NV divided by P. Then this P can be written as with the acceptor atom, right? So then KT will be equal to NV divided by NA. Okay. So this is the third formula that we are getting for. So we have completed the analysis that for intrinsic we have calculated it, and then for Fermi n-type we calculated, then p-type. So three formulas we got it. So here also same thing. If an acceptor energy level atom is much greater than NV, then it is a degenerated p-type. Degenerate p-type. Okay, so this is one important thing. Okay, I hope it is understood for you guys. So in this next class, we can even get deeper dive into some of the relation. Like I will draw a Fermi energy level with accommodating all these values, and you guys will be able to understand clear-cut picture of it. So what the thing we have seen is the first thing we have calculated the intrinsic Fermi level, where we equated the P which is equal to N. From the both the formula we are able to get this one. So this is one of the very important things. So keep a note of it. So intrinsic Fermi level will be equal to E mid whenever these conditions got met. So then second thing is for p-type we calculated, n-type we calculated it. So we have get a wonderful formula of relation in the energy band diagram. So then the third is the p-type we have found, and also we found for the degenerated semiconductor condition. I hope the lecture is very informative for you guys. So if you guys think it is very informative, please like, share and subscribe the channel, so that I will be get motivated and posting more videos like this. So we have also already started an initiative on the AI course also. So please watch those things also. So we are giving a very good detailed analysis of everything. So that we are doing project analysis and also foundation course. So it will be very helpful for college guys and even for the passed out tech guys also. So please watch and subscribe the channel, so that I will be doing more things like this. Stay tuned for the next lectures. Thank you. Bye.